Part D at the first view might look like an integration by parts. We have an x term here, but then we have e to the x squared. Finding an antiderivative of e to the x squared is hard, so integration by parts isn't actually very promising. Instead, we can do a straightforward substitution. We substitute u is equal to x squared, so du is equal to 2x dx, and with this substitution the integral becomes e to the x squared becomes e to the u, 4x dx becomes 2 du. Now we can easily find the antiderivative here, namely this is just 2 e to the u, and substituting back we get 2 e to the x squared plus c. Problem E at the first glance might look like trigonometric substitution, but this is actually rather hard to do. Instead, let's look at this. This is a function which is prototypical for a term resulting out of partial fractions. How do we deal with this? Well, we split this in an integral with x, in a summand with x in the numerator, and we split it up into the summand with 3 in the numerator. Now we can integrate the terms separately. The first term, we do a substitution. We substitute u is equal to x squared plus 1, so du is equal to 2x dx. So we get from the first term the int 1/2, because we don't have this factor 2 here, integral 1 over u du. The second term, we know an antiderivative here just from looking at it. This is 3 times 1 over x squared plus 1. Looking in the table, we get simply 3 times inverse tangent. The remaining integral over 1 over u is very easy. This will give us a logarithm. Finally, substituting back, if you wonder why the absolute value has gone here, well, x squared plus 1 is always positive, so we never will get a negative value here. And that's the antiderivative. Finally, in part F, I know you all waited for it already, we have a proper trigonometric substitution. We have 9 minus x squared, so we have something minus the x squared term, so we will do a sign substitution. We substitute x is equal to 3 times the sine of theta, and dx therefore is equal to 3 times cosine theta d theta. Let's do this substitution. Here we've substituted the x cubed term, we've substituted the x squared term, and this is what we came from the dx. We can simplify this. We can pull a common factor 9 out of here. Pulling it out of the root gives us a 3. This 3 will cancel with a 3 here. And we have the square root of 1 minus sine square. Well, that is the cosine. That was basically the reason for this particular trigonometric substitution. So we get this integral. The cosine in the denominator cancels with the cosine here. So we have simply 27 times the integral over sine cubed of theta d theta. How do we do this? 3 is an odd number, so we write this as 27 times the integral 1 minus cosine squared. Now we substitute cosine and we get the integral over 1 minus u square du. Here the antiderivative again is very easy because we have a polynomial. We get 27 over 3 u cubed minus 27u plus c. Substituting the u back, we get cancelling 27 over 3 to be 9. Now we need to do the theta substitution backwards. We need to write it in terms of x. This is the point where we will be using the triangle. So how does our triangle look like? If we have the angle theta here, a right angle here, we had that the sine of theta is x over 3 because x was equal to 3 times the sine of theta. So sine of theta is x over 3, so we have side length x here and side length 3 here. This gives us for the remaining side a length of the square root of 9 minus x squared by Pythagoras theorem. So now we read off the cosine. Cosine theta therefore is the square root of 9 minus x squared divided by 3. Plugging this back in, if we want, we could simplify this first term a bit further. And we found our antiderivative.